We're going to do quite a bit of these problems here for the simple fact that they're pretty quick and it takes a little getting used to of how to do these. So a few examples are definitely necessary to accomplish this. So the first one says, for the following exercises, evaluate the base B logarithmic expression without using a calculator. So it wants us to do this by hand. So there's a few processes that I learned over the years. And I think this one is probably the one I've seen the most helpful overall, not for everyone, but overall. So essentially we say, okay, this is log base 3 of 1 over 27. And then just give it a dummy variable. We'll call it y. Now the reason for this, because dealing with logs by themselves is hard to wrap our heads around, because it's a different sort of operation altogether. And we'll see why that is later, and I'll talk about it. But anyways, this is the functionality of it. I'm turning it into its exponential form. Now we've talked about equations of this form already, about how can we solve them. Now how we solve these types of equations is we get the same base on both sides. And if you noticed on the left, it's just already in that form. And on the right, it's really 3 to the negative 3. Hopefully that's evident. Remember, you flip it to the bottom, and that's what that does. And it makes the exponent positive. Now it's 1 over 3 to the third. And 3 to the third is 27, because 3 times 3 is 9 times 3 is 27. So this gives me the answer that y is negative 3. And if y is negative 3, my log base 3 of 1 over 27 is also negative 3 because it equals y. So that's how we use that dummy variable to set it up in the equivalent form, so that we can actually get a value more algebraically, as opposed to just trying to work with the logs or manipulate the logs. So that's our first one. That's number 42. Now let's take a look at 43. And again, it's the same thing. And that's why I told you in the previous video, get the process down with this equivalent form, because that's going to be a lot of what we're dealing with all of these problems, not just evaluating. All right, so let's take a look at this one now. So this says log base 6 of square root of 6. So I'm going to say equals y. So then that's going to be 6 to the y equals the square root of 6. And hopefully you know the square root is a power as well. And I hope you remember that it's the 1/2 power, because that's like an index of 2 out there. And it'd be 1 over 2. So that's how that works. And then I can simply say then y equals 1/2. So that tells me the log base 6 of square root of 6 is 1/2, because if y equals 1/2 and y equals the log base 6 of square root of 6, then I can say that the log base 6 of the square root of 6 is 1/2. All right, let's take a look at 44 now. Again, these are short problems, which are kind of nice compared to some of the problems we've seen in the past, but very different. Okay, now here's an interesting one. Log base 2 of 1/8 plus 4. So what we're going to do is we're just going to talk about this piece first, and essentially when we find that value, we're going to add 4 to it. That's all this is telling us here. Nothing more complicated than that. Okay, so I'm still just going to take that first piece because I want to understand or know what log base 2 of 1/8 is in terms of its value. So I'm going to say equals y. That's going to be 2 to the y equals 1/8. So that means 2 to the y equals 2 to the negative 3. And again, if you're not sure about those negative exponents, play around with them, do some problems, get comfortable with them, because you're going to see them a lot here. So this is y equals negative 3. So that means this whole piece right here is equal to negative 3. So really what we have there is, and I'm going to get rid of this piece here just to get it out of the way. We don't really need it anymore. And I just wanted you to see where it comes from, just using that definition there. Okay, so anyway, so we really have now negative 3 plus 4, and that equals 1. So our answer for this one is 1. Our answer for the last one was 1/2, and then the first one was negative 3. Okay, so there's the first 3. Now let's take a look at those second 3 now. And it doesn't really change, but again, the numbers change, and that might seem completely different to you. So now for 47, there are a few different ideas here, though, that I must address before we continue. And one of them is when I see log of a number, call it A. When I don't see a base here, there's no base we see here, it's understood to be 10. And the reason for that is, think about what base system we use, like numbers, like 1, 2, 3, and then we go to 10, then we go to 100, then we go to 1,000, 10,000, 100,000. Those are 10 base system that we use. So that's why when I don't have anything there, it's understood to be 10. Okay, so this is really saying, because I don't see anything here, log base 10 of 0.001. That's what that's really saying. So to understand it that way, I'm going to say, hey, let me set that equal to y then, because that's what we do. So for this one, we're going to say 10 to the y equals, and I'm not going to write 0.001. I'm going to put 1 over 1,000. To me, that seems a little easier to deal with, just from the last problems that we worked through. So then, what does that mean here? I can write this in terms of the same base, right? Because it's 10 base, actually. This is 10 to the negative 3. I think they love negative 3 with these problems. So that tells me this answer is negative 3. Okay, now 50. Here's another one that's a little different that we may have not seen yet. The ln. That's called a natural log function. And I'm going to write this down here. So the ln of x is equal to the log base e of x. Now, I don't know if you're familiar with e, but e is what we call the Euler number. And Euler is spelled with an EU, so it's not the conventional one in English. So anyways, so this e is an approximation like pi is. They call them transcendental numbers. And e is approximately 2.718281828, and it honestly keeps changing, and there's no pattern to it, but this is an approximation of if you typed it in your calculator. So like we have the square root of 3, the square root of 2, which is 1.41, or just things like this. E is one of those numbers that is irrational and just keeps going on forever, like pi is. So we can treat it the same way. It is just a number, so don't be alarmed. So for 50, if we have the ln of e to the 1/3, okay, then I'm going to set that equal to y. But first, you may want to think of it as log base e of e to the 1/3 equals y. Because then I can say e to the y equals e to the 1/3, and that makes these very simple to work with as well. So that means y equals 1/3. And we're going to talk about this idea a little more later too. So this answer for number 50 is 1/3. But again, I had to understand that the ln of x is equal to the log base e of x. So put this right here, this fact, in your notebook, because you're going to see that a ton. So something to think about. Okay, now the last one here, number 51. There's our ln again. Ln of 1. So I'm going to say equals y. And remember, you still might not be comfortable enough yet, but this is really log base e of 1 equals y. So that's e to the y equals 1. So would you guys agree that, what can I put in terms of that exponent so that I get a 1? Hopefully you guys caught that right away. You should know that it's going to equal 0, because anything to the 0 power is 1. So the nice thing about it, for any log function, taking the log of 1, I will always get 0. So that's something nice to take along with that. If I take the log of something and it's 1 in there, whatever it is, then I can say that it equals 0 instantly for that reason. All right, so there's a bunch of problems that we just went through here. Hopefully it's a big help.